So what are the main reasons to use an event-related design? Well, there are a number. First, it allows you to randomize the condition or the stimuli order. And the reason for doing this is that sometimes block design can lead to confounds, particularly cognitive sets. Let me give you an example. And this is just a simple toy example, but imagine you are my participant, and I put you in the MRI machine, and then I show you some pictures, and your job is just to look at the pictures. So here I'm showing what a block design might look like, and on this axis is time. So you're my participant, and now I will show you the actual images you would see, okay, in this block design. So this might be block 1, and then we put a little break in there, so a little pause. Now I'll show you block 2. And then there would be another pause, and then I would show you again images from, there would be block 3, and that would be one of these 2 types of images. But it's pretty transparent what's happening. After the first 2 blocks, as the participant, you already know that really what's happening here is that there are some pictures that are unpleasant or scary, and other pictures that are pleasant or neutral and non-scary. And see, the problem is that if your participant understands transparently what's happening, it might lead them to adopt cognitive sets, to have specific expectations. So maybe, for example, after you see these 2 blocks, imagine you have a participant who really hates scary pictures. And of course, this is an extreme example, but let's take it. Imagine you have a participant who really hates, ferocious animals. Now they know, after the first 2 blocks, they understand that if the first picture is a scary one, the next 2 pictures are also scary. So your best strategy is, if you see the first one that is scary, just close your eyes. Stop looking for a few seconds and then look again. And if you're lucky, you're either in the break or you're now in a pleasant block. So you can see how, of course, as I said, this might be a slightly extreme example, but you can see how having these big blocks makes it transparent as to what the manipulation is across the blocks. And so the participant can, if they wish, adopt, either develop expectations or adopt strategies that might play against what you are trying to do. In our crazy example, in our sort of extreme example, what would happen is that you would end up comparing viewing pictures of pleasant images to closing your eyes during the unpleasant images. Or maybe somebody who also doesn't like these unpleasant images, they might coach themselves mentally through the images and say, who knows, develop a strategy where they say, oh, it's just a picture, calm down, it's just a picture, calm down, it's just a picture, calm down. And now when you compare pleasant versus unpleasant images, what you're comparing is looking at pleasant images versus looking at unpleasant images and talking repeatedly to yourself to calm yourself down in response to these images. So the end result of what you're looking at in the brain is not what you think it is. So for this reason, it might be best to adopt a slow event-related design, which I'll show down here. Again, if you were my participant, maybe this is what the order of things would be. And as you can notice, there is a certain unpredictability as to what is happening next. So your participant might still see a picture of a spider and then just say, okay, I'm going to close my eyes now for the rest of the experiment. They could do that, but it wouldn't bias systematically what you're doing. You would just be comparing viewing nothing to viewing nothing. So this type of design is meant to, this type of slow event-related design is meant to minimize the ability of participants either to develop expectations or to develop strategies that you might not be aware of and that might play against you when you analyze the data. Okay. So it's very important to reflect on the psychology of how your participants would react to seeing stimuli. So if you're designing your own experiment, be your first participant in the lab. Just go over it, imagine you were the participant, how do you respond to the stimuli? You might discover that it's easy under some circumstances to come up with expectations or cognitive strategies. And your job as the experimenter is to try to find the design that best minimizes extraneous expectations or extraneous cognitive strategies. Event-related designs happen to be good at avoiding clear expectations or clear cognitive strategies. Now, a second advantage of event-related designs is that sometimes you might not know whether a given trial is condition A or condition B. So sometimes you only find out either during the experiment or after the experiment whether a given trial is condition A or condition B, or when condition A starts and when condition B starts. Let me give you an example. In 1998, Wagner and colleagues were interested into what is the difference in the brain between items that you view and then remember versus items that you view but forget. What is it? What correlates with remembering versus forgetting something that you have seen? Their experiment went as follows. Again, you're the participant. You'd go inside the MRI machine, and then you'd be shown at a slow pace a number of words. And your job as you view these words is to respond to a button press, whether you think the word is an abstract word or whether it's a concrete word. So that's all you have to do inside the MRI machine. And you view, let's say, 50, 60 words. And then you come out of the MRI machine and the experimenter says, oh, I forgot to tell you. Now there's a memory test. And so what the experimenter would do is they would show you, we said these were 60 images, 60 words. So let's say now you're shown 120 words, 60 of which are exactly those that you saw inside the MRI machine, and 60 of which are completely new words. And your job is to recognize which of these words you have seen in the MRI machine and which of these words you have not seen in the MRI machine. And so once that happened, as the experimenter, you can now sort the trials between the remembered items, so those that were shown in the MRI machine, and that the participant correctly said, I remember this one, so a hit, and the forgotten trials where although the word was shown inside the MRI machine, the participant didn't remember it and thought it was a new word, or a mistrial. And now you can allocate individual trials to condition A, remembered, or condition B, forgotten. And now you can do your fMRI analysis of interest, which is remembered items versus forgotten items. And see, as I was saying earlier, the problem here is that you don't know beforehand whether a given item will be remembered or forgotten. Needless to say, you cannot block items that will get forgotten and then block items that will be remembered. You will only know after the experiment, when the participant does the recognition memory test, whether any given item goes in category A, remembered, or category B, forgotten. Another, and in fact, just to sort of give you an example of what happens here, there are two parts of the brain that seem to respond differently, or rather that were engaged differently while participants were looking at remembered versus forgotten items. Turns out in the temporal cortex, in the parahippocampal and fusiform gyri, there are two areas where when the items were remembered, the activation was stronger. The bold response was stronger in this purple color compared to items that were forgotten in the green color. So this allowed Wagner and colleagues to ask, what is the difference? Why is one item remembered and the other one is forgotten? Now, another example of a similar circumstance is this beautiful and very clever example by Frank Tong. Now, he was interested in perception. And one way of studying perception is to show an ambiguous stimulus, such as this one, also known as which which triggers a rivalry between two images. As you can see, there's a face in one color, and there's a house in a different color. As the participant, you would have on you glasses where one lens is green and one lens is red. In other words, one eye is seeing a house and the other eye is seeing a face. Typically, we know two objects cannot be in the same place in space. So what happens to you from the perception point of view, you will sometimes see a face and sometimes see a house. So as the participant in this experiment, your job is the following. You're placed in the MRI machine, you're shown this image, and then you're told, start by looking at the face, and then every time your percept changes to the other object, click. Okay. So for example, you would start by seeing by focusing on the face, then all of a sudden, now suddenly the center of your perception becomes the house. And so you click to let me know that now what you're seeing is the house. And then suddenly it switches again to the face. And so you'd click again and let me know that now you're seeing a face. Mm-hmm. So in this way, you, the participant, are revealing to me when you are in condition A, the face, and when you are in condition B, you're perceiving the house. So until you tell me, I cannot tell whether you're in condition A or condition B. So I cannot beforehand block or assign trials to condition A or condition B. I need to wait for you to tell me when is condition A and when is condition B. Now, what would make for a good baseline for this experiment? Well, this is why I always think of this experiment as a very clever one. So what Frank Tong did is, now that he knows that, for example, you spent 5 seconds, you perceived the face, then for 10 seconds, you perceived the house, then for another 5 seconds or 6 seconds, you perceived the face, and so on and so forth. What he did is, as a baseline trial, he actually showed to the participants faces and houses exactly for the same duration. So now that I know that how your perception went, in the baseline, in the comparison, in the control test, he would actually show the face for, let's say, 5 seconds, then actually show the house for 10 seconds, and then actually show the face for 6 seconds. So this way, you can the two stimuli during the rivalry condition and the control or non-rivalry condition are exactly matched. What you as the participant are perceiving is exactly matched. What's different is that in the rivalry condition, you had these spontaneous changes, and you were seeing both stimuli all the time, whereas in the non-rivalry condition, your stimulus, your perception was not spontaneously changing, was exogenously changing, which means the stimulus itself was changing. And so this way you can study what's the difference between these spontaneous changes versus non-spontaneous changes, or these perceptual changes that are endogenous versus perceptual changes that are exogenous. Now, another good reason for employing event-related designs is that sometimes you just cannot block certain events. Sometimes the type of event you care about just cannot be blocked. And this is typical of so-called oddball designs. Let me give you an example. Let's say, again, you're my participant. This is time. And I'll just show you the timeline of what you would see if you're the participant in the MRI machine. Now, if you blinked and missed it, this was the oddball. And see, the oddball is defined as a rare event that violates a standard. The standard, obviously, the expectation is these red dots. And then suddenly there's another image that violates what you are expecting, that triggers an event which we refer to as an oddball. And see, if you want to study oddballs, you cannot block oddballs. In order to have an oddball, you need to first establish a standard so that you can then violate it with the oddball. So there's no sense in which you can create a block of oddballs. The very definition of oddball requires you to have these standards so that you can get the oddball. So there's no way in which you could block oddballs inside the block and then block non-oddball events. So if this is what you care about, you just cannot use a block design. In this case, every single trial needs to have this series of standards so that you can violate them. Now, there's another important aspect of experimental design, which is knowing exactly when your stimulus of interest starts and ends. And see, sometimes it's just very easy to know what that is. For example, if you're showing a picture of a face, the onset and offset of that picture might be the onset and offset of the cognitive process of interest. Other times, you have to be very careful to know exactly what your event of interest is. For example, let's say that you're my participant, and what I need you to do is some words will appear right here over the arrow. Please read them as they appear on screen. Okay, ready? Here we go. And now you might have noticed that if you were reading along, something happened by the time you got to was. And this type of sentence is known as a garden path sentence because it leads you down the wrong path. You probably were reading the sentence and thought the man returned to his home, and you were imagining somebody who was walking towards their home, and then you heard was happy, and that just doesn't work. So that might have caused you to have to go back and say, oh, the word return doesn't mean that somebody was walking back to their home. It means that someone returned a man back to their home. And the person who was returned to their home was happy. So see, this highlights the importance of knowing when your event is, because in order to properly analyze the cognitive processes you care about, you need to know what the event is. For example, if I said my event starts here and lasts all the length of the sentence, and then we looked at the neural basis at the neural basis of that, what cognitive processing are we capturing? Well, all sorts of. We're capturing visual processes. We're capturing low-level and high-level visual processes. We're capturing the processes that associate letters with sounds and with meanings. And then somewhere in there, there also is something about reparsing a sentence, which happens down here. But of course, this little event that is happening down here is drowned amidst all the other things, all the other cognitive events that are happening for you to interpret the sentence. So if what you care about is what does it take to reparse a sentence, once you realize that you've understood it incorrectly, then your event is actually here. And what you truly want to analyze is this time period, not all of this. So this is what I mean. Knowing when your cognitive process of interest happens is crucial. So you need to know, you need to be confident as to what is the timing of your cognitive process of interest. So we've seen a number of advantages of event-related designs, but I don't want you to think that block designs are outdated. They're not. They're used all the time, even today. And there are a number of reasons for it. First, block designs are statistically just much more powerful. You can think of it this way. Event-related designs is like you trigger the brain, you give one trial to the brain and you look at the response, and then another trial and you look at that response and you can average them all together. But if you're doing a block design, it's like you're hammering the brain with a certain cognitive process, and you hammer it and you hammer it and you hammer it. So you will definitely get a strong response from the brain. If you were showing pictures of faces for 30 seconds, you're really engaging all the parts of the brain that it takes to process faces, and you're getting them engaged for 30 seconds. It will be easy to detect what parts of the brain care about this cognitive process when you compare it to either a rest baseline, so looking at the blank screen, or a different condition. Whereas if you're doing event-related, You're kind of triggering the brain one little drop at a time, which is wonderful for the reasons we just discussed, but is not quite statistically as powerful. Also because, as we will discuss in just a moment, you get to have fewer trials. Now, there are other factors that might play into deciding not to use an event-related design, and these are often psychological in nature. For example, sometimes it's not as easy to start and stop a cognitive process. It's easy to start and stop looking at a picture that is in front of you if the picture just offsets. So once the picture is gone, it's gone. There's nothing sort of, you don't have much of a choice. But some cognitive processes don't start and stop that easily. A typical one that I myself have used often is mental imagery. If you were to ask somebody to close their eyes and imagine something, let's say, imagining playing tennis, it takes some time to build that type of imagery and to engage with it. It's not something that you can start and stop easily in the span of a few seconds. So certain cognitive processes are better triggered and better elicited in a block design. And finally, you should also keep in mind that if you use event-related design, there is a risk that you could complicate. If your design is complicated, it might be difficult for the participant to follow what they have to do. It might be difficult for them to keep switching between condition A and condition B. Particularly if each of these two conditions sort of has a different set of instructions and has a different set of things that the participant has to do.